Hello and welcome to my talk, Forced Imbibition and Uncertainty Modeling using the Morphological Method. My name is Pitt Arnold and I'm a simulation engineer at Digital Rocks at Wintershall-Dea, and today I'm going to present parts of my PhD thesis conducted at the Montana University in Leoben. Before starting the talk, I would like to thank all of my co-authors for their continuous support. Before going more into detail about the forced imbibition modeling, I would like to do a qualitative comparison and positioning of the morphological method used in this work with other post-scale simulation methods such as Poe network modeling and Lattice-Boltzmann method. In the graph, I'm just showing the most common types, so please note that there's also other methods you can be using for modeling on the Poe scale. So what you can see on the y-axis is the abstraction of the Poe space going from low to high. Whereas on the x-axis, you're seeing physics in the simulator from a simplified to a more detailed physics which are applied. So this is just a qualitative comparison between the stuff. So what do we mean with abstraction of the Poe space? When we talk about methods like morphological approach or Lattice-Boltzmann method, we are actually working directly on the Poe space. So what we are using is, for example, then you get images from a micro CT, and then you segment the images, and you can work directly on the segmented image. Whereas in Poe network modeling, you have to apply some sort of extraction algorithm. So with this, then the abstraction of the Poe space increases, meaning that you use not the real work structure anymore, but you use, for example, a more simplified structure such as sticks and balls in the most simplistic case. When referring to the physics in the simulator, we are talking on the one hand about processes such as the interaction at the fluid interfaces, which can be modeled, for example, in the Lattice-Boltzmann method, but also about adding a time scale, which is, for example, in dynamic Poe network modeling or Lattice-Boltzmann method present. And please note that this is just a qualitative comparison between the methods and that this is not a rigid boundary between each of them. So what we have been doing in this work is that we wanted to extend the physics of the morphological approach as it was present within this work, meaning that we wanted to account for not having a timescale when modeling a forced imbibition process, where this is quite of importance as you want to account for the sequence of advancement of your free phase contact lines. You might have asked yourself, why is it so attractive to use a morphological method, even though there seems to be already other simulation methods on the Poe scale which apply much more physics or which have a more detailed level of physics. That's when you have to refer to the computational costs. So a Lattice-Boltzmann method takes a lot of computational costs compared to, for example, a quasi-static Poe network modeling or the morphological method. And here I'm just also showing a qualitative comparison as it is not a black and white area, since for some of the methods you use more GPU-based simulations, for the other more CPU-based simulations. So you cannot directly compare them. However, what you can say is that using the morphological method is very time effective and that you can use it on large structures. So why is the morphological modeling approach so computationally attractive? So how it is working is that it's just working with a basic morphological operations such as dilation and erosion on the direct Poe scale. So on the right hand side you can see a grain, and which is in gray, and some sort of radius R1, which in this case is a dilation around the grain A, or you could also see it as an erosion into the pore space. And by this we can identify the pore throats purely on a geometrical basis. So as you can see, we have this dilation radius R1 around our grains, and where they meet from the size, you can see that we have identified the pore throat radius between the first two grains. And after the identification of that pore throat, you can connect that to a saturation. So meaning that if you would be invading from the left-hand side, that as soon as you go below this dilation radius, R1, that you are invading this pore space right-hand side of these grains. And with this, you can connect the pore volume or saturation to a certain PC by using the Young-Laplace equation showing on the bottom. Decreasing now our blue dilation radius R1 to R2, for example, we have identified the pore throat of our next grains, all right? And while you decreased the radius, your capillary pressure increases because it's inversely proportional to the capillary pressure. So it's 1 over R. And we have now a new volume which is open for invasion, so also our saturation is changing. So what we haven't talked about it yet is that our grains can have different wettabilities. And to account for that, what we can do is that you just multiply this dilation radius you have with a certain contact angle. And then what you can see is that now with the same dilation radius, but having a different wettability, our first pore flow is already open for invasion for the same dilation radius step. So what you can see is on the capillary pressure curve on the bottom that our blue dot would be now shifted, so we have a saturation change for the same capillary pressure. And this allows us that we have different pathways for the invasion when applying multiple contact angles. So how do we go now from our morphologically populated model, basically our capillary pressure we have, to flow properties such as relative permeability? So on the left-hand side, you can see, just as I explained before, our morphologically populated model, which is initially filled by a wetting phase. In this case, it's just a blue wetting phase, could be water, for example. And you have on the left-hand side an inlet and on the right-hand side an outlet. So what you're doing is you do this dilation operation, and then you check for connectivity of the invading phase, which in this case is then the green here. And in a more light green, you can do then again a dilation operation around your invaded phase. And with this, you have established for capillary pressure step the population of the model. Then once you have done this, you check for connectivities, and you can then simulate on each of the connected phases your effective permeability. So you have on the top, for example, it's just the blue phase connected. On the bottom, you have the green phase connected, and then you can divide each of the effective permeabilities of each of the phases by the absolute permeability of the entire structure. And with this, you're getting your relative permeabilities for different saturation steps. So far, so good. The problem, however, was that we initially were just able to model a single process, such as a drainage or a spontaneous imbibition. And we know from experiments and from reality that imbibition might also have a forced process involved and does not necessarily stop after a spontaneous part. And therefore, what we needed to assess is how can we now combine such a single process with another one, basically combining a spontaneous with a forced imbibition process. And here on the right-hand side, you see basically what was initially we would be getting out. So we had a drainage, which refers to the displacement of the wetting phase by the non-wetting phase until you reach a residual saturation, and that is then your starting point for the imbibition modeling, where we are displacing the non-wetting phase by the wetting phase, and the spontaneous imbibition then stops at the point when you have a capillary pressure of 0. So the question was, how can we now connect a forced process to that, or how is it even connected? So what is the problem when you just model a spontaneous imbibition? First of all, you get just a limited saturation range for your capillary pressures, and then hence also for your relative permeabilities, as you saw earlier, that they are connected. And what is happening is that you get an early cutoff of your relative permeability data, and it was already shown in earlier studies that this leads to a mismatch to actual experimental data. So on the right-hand side, you can see a steady state data set. So all of the blue and red dots, they are from experimental data set by Berg et al., which I will revisit later. And the black crosses show the relative permeability side results when using the original method. And you can see, first of all, that just not even half of the saturation range was reached, but also that there is a great mismatch between the actual values. So what was the idea? We needed some sort of stopping criteria to avoid this disconnection. You can see of the oil phase to so the crosses compared to the red squares on top. So we needed a stopping criteria to avoid this disconnection early on, and needed to couple it to some sort of forced process because you have a forced imbibition which is happening there. So how did we implement such a stopping criteria? Was by the introduction of non-wetting material. Wettability modeling is very complex, And therefore, we chose two different approaches. One is the stochastic and one is the deterministic one. On the stochastic one, what we are using was a stochastic field where we have different region sizes and also solid volume percentage, which we were distributing within the system. So you can see there's the original structure in gray, and then you see dots in this golden color and in different gray scales. And there you can see that on the one hand, we used very small spot sizes. So in this case, it was 10 micrometers, or also larger spots to distribute different materials. And we would be using not only one or two materials, but also up to 4 different ones to investigate the influence of the of having multiple materials instead of just one. And then on the other hand, there was also the deterministic modeling approach used. So here we want what is done is mimicking rather an aging process. So at the end of the drainage process, process distribution was done, and then you have to define a certain threshold for the implementation of the non-wetting material. In this case, it's called pore space considered. This means you can see in picture number 2 on the top right that 50% of the pore spaces would be now considered. So leaving just the largest 50%. This is also a very important note. So just the largest 50% would be considered for the implementation of the non-wetting material. And then if these pores were filled with oil after the drainage process, or with the non-wetting phase after the drainage process, then in step 3, around these big pores, then the non-wetting material is implemented, leaving you with a final structure of having the non-wetting material then in these larger structures if they were in contact with a non-wetting phase at the end of a drainage. So here we are showing both of the approaches on a 3D level, because in 2D it might have looked a little bit more weird, or you might not see certain features. Therefore, you see on the left-hand side, if you use the stochastic approach and you use a small region size, it's just randomly adding these small blobs within your structure. And it can happen that if you have a very high percentage of you adding them, so for example, if you would add 60%, of the material you would turn into non-wetting, then you would see that, or it can happen that smaller blobs are connecting to a bigger one. And then on the right side, you see the region size 100. So it can be that spaces which might be populated by choosing a smaller region size are not populated, but then an entire region, and in this case on the bottom, is entirely populated. When using the deterministic approach, as I said, you have to say how much of the pore space you want to consider for the implementation of non-wetting material. And also it's when you apply it with a higher number, then it's still also prioritizing the biggest pores first. And therefore, on the next page, you can see in more detail that if you would use a high value, that the small pore gets populated with non-wetting material, whereas on the top, when you use a low value, you don't get any population within the small pore. So how do the results look for these different population methods? So on the left-hand side, again, you can see the stochastic approach, and on the right-hand side, you can see a deterministic approach. So what you can already see that when using stochastic approach, we applied this non-wetting material already at the start of the drainage. So also the drainage curves are affected by it. And the color code, you see that black is the least amount, whereas blue is the most amount. And the squares show small region sizes, whereas the triangle show large region sizes. In between, the yellow would be showing if you use the original method just with a single material, not implementing any of the non-wetting material. And what you can see already is that the more of the non-wetting material you implement, the earlier you're switching from a spontaneous to a forced process. And also you can see that when using smaller region sizes, the effect of this shift is stronger compared to a large region size. On the right-hand side, you see the deterministic approach, and there we're just using one single value for this pore space considered. But what you can see in here that we have also worked out if these trends are true then for different contact angles of the material. And you can see in black is a contact angle of 0, so strongly wetting, whereas then green would be 60 degrees, where it would indicate a less wetting condition. And with 10 and 40 degrees, we have something in between. In order to quantitatively judge these changes, we computed different wettability indices. One is the AMOD wetting index, which compares the spontaneous saturation range to the total saturation range of our imbibition process, and which means that a low value indicates that it's mainly dominated by the spontaneous process, by the forced process, whereas a high value would indicate that it's almost entirely consisting of the spontaneous process. The wettability index just compares the areas underneath the curve between the spontaneous and the forced inhibition, meaning that the value above 0 indicates that the spontaneous process, so the work done by the spontaneous process, is higher than the one of the forced process. On the left-hand side, you can see the results for the stochastic approach, and you can see that for a small region size and a high solid volume percentage, so a lot of non-wetting material implemented, we have strong non-wetting conditions, whereas with increasing region size and also decreasing solid volume percentage, we get more of a wetting condition. We also plotted the data against the pore throat diameter. So you see on the bottom here you have the region size, but also the pore throat diameter size. And this shows that the data is very sensitive when it's within the sizes of the pore throat diameters, meaning that this data, so the stochastic approach, is very sensitive to the structure itself, meaning that you cannot say for every structure that you could use the same values to get the same results. So you have to figure out what is the resolution and pore throat diameter distribution within your structure. On the right hand side, on the other hand, we should see the results for our deterministic approach. And here we plotted it against the pore space considered, meaning that the more pore space is considered, the more also of non-wetting material is introduced. However, please note that this is not a linear relationship, meaning that if you consider 50% of your pores for the introduction of non-wetting material, it doesn't necessarily mean that there's 50% of non-wetting material implemented, as you can see then plotted against the right side. However, what you can see is that both of the indices, so the wettability and also the AMOD wetting index, both decrease with increasing pore space considered, meaning so the more of pore space is considered for the implementation of non-wetting material, the less of a wetting condition we have for the entire system. And here you just see both of these effects I just described indicated that with an increasing solid volume percentage, so more of a volume fraction which is used for the implementation of the non-wetting material, the wetting indices is going down. Same goes for the increased pore space considered, and with the red line, it's just for the wettability indices, which compares the areas underneath the curve, showing as everything below would be non-wetting and above would be considered as wetting. So what have we been observing? Both the stochastic and deterministic approach show certain trends when more of this non-wetting material is implemented. The stochastic approach changes the drainage as well, whereas the deterministic approach is more like an aging process, which is applied at the end of your drainage process. You can do some uncertainty modeling by the variation of the pathways, so meaning that the more you use of it, or if you change, for example, the region sizes, you will open up different pathways for the invasion. Both of the methods show the right physical trends, meaning the more non-wetting material is implemented, the less of a wetting condition our systems show. However, the question which is posed is, how does this compare to reality? And for this, we revisit the early on shown data from Berg et al. So what you see again in the full square dots are synchrotron data. So this is the actual fluid distribution on which we have conducted the Stokes simulation, and we have compared it then to the morphologically populated data. So there you can see again our black crosses, though this is the original method where you have a strong mismatch. And then in the next slide, I will show the comparison to our new approach. Here you can see now how the experimental data is comparing with our simulated data using the new implementations we have discussed beforehand. And here you can see that we talk about a deterministic, the stochastic, and the full cycle approach. With deterministic and stochastic, we are referring just to the implementation of the non-wetting material from beforehand, whereas with the full cycle, I'm referring to a full drainage and imbibition modeling from the beginning. So there was two approaches we have taken. One is taking the experimental distributed state at the residual saturation and model from there on the experiment. So this is the deterministic and stochastic approach, and the other was just taking the dry sample, not having it populated by any fluid, and modeling the whole drainage and the imbibition process. And what we have been observing is that on the one hand, the more dominant the forced imbibition modeling was, the better results we got compared to the experimental results, and that we had to avoid strong wetting conditions. The problem if comparing relative permeability curve is that they are non-unique. So this means that I could have two connected pathways which have the same effective permeability, even so they might be populated in a different part of the system. And therefore, to get further insight, we actually computed some topological measures. In this case, we compared the normalized Euler number between the experimental and our simulations. The Euler number is computed by counting the objects within the system and subtracting any loops and add any inclusions. So here on the left-hand side, you'd see different objects and the according Euler numbers to it. And since we didn't want to put too much weight on very small clusters, which do not matter for the flow too much, but which are still present, we used a normalized Euler number. So what we did is we computed the Euler number of the cluster, multiplied it by the volume of this cluster, and then we divided the sums of each of those with each other, as you can see on the bottom left. And with this, you can see then the results on the right-hand side. So there's the non-wetting phase in the middle, and on the right side is the wetting phase. In blue, you can see the normalized Euler values, and in red, the linear relative permeabilities. And what you can observe is that for the non-wetting phase, our deterministic stochastic approach quite well match the Euler number of the non-wetting phase, which is because you start from the same distribution as in the experiment. Whereas for the full cycle, we start from the drainage distribution, so our fluid distribution from the drainage process, which is also modeled. And there you have already a mismatch from the beginning, meaning that in our simulated drainage process, we end up with more smaller clusters also within the system. For the wetting phase, on the other hand, we see that the deterministic and the full cycle process quite well match the Euler characteristic of the non-wetting of the wetting phase, whereas the stochastic approach deviates from that. So all in all, we could show that this new approach is working, as we could see that we matched it to experimental data set, and that we are now able to do uncertainty modeling by varying different contact angles and by changing the size of the and volume of the non-wetting material implemented either by the stochastic approach and by the deterministic approach. And with this, I want to close my talk and thank you for watching it. If you're interested, we just published a paper about the forced imbibition and uncertainty modeling using the morphological method, which is open access. In Advances in Water Resources. And I also want to thank Steffen Berg for his helpful discussions and for guiding me. And feel free to ask any questions. And thank you.